Welcome back. We are going to talk about one of the most important theorems in all of mathematics, which is the Fundamental Theorem of Algebra. Now this says every n-degree polynomial has exactly n complex roots. That's what it is. It sounds very simple, but it has profound implications. One of these is that if we have a function like f of x equals x to the 7th plus 5x squared minus 8, there are 7 numbers, 7 zeros, to this function. Now, they're probably going to be irrational because I just made this function up, but irrational numbers are still complex numbers. So if we know it's a 7th degree polynomial, we know we're going to have 7 answers. Just like if we have a quadratic function, for example, x squared minus 8x minus 16, we know that this will have exactly 2 solutions, because the degree tells us how many solutions we get. Now you might be thinking to yourself, I already knew this, and it's quite possible that you did, but you probably didn't know that it came from the Fundamental Theorem of Algebra. What this also tells us is that every polynomial can be written as a product of linear factors. So consider the polynomial f of x equals x squared plus 16. Now, this has imaginary solutions. So we wouldn't necessarily factor this expression, but if we identify that the roots are negative and positive for I, then we could write our polynomial as x minus 4i times x plus 4i. So this would be an example where we have a polynomial with imaginary zeros. Imaginary numbers are complex numbers. And we can again write it as a product of linear factors. This also affirms what we said in our last video, that the sum of the multiplicities of all zeros adds up to the degree. Because if a zero appears 5 times, that's 5 zeros, and that contributes 5 to the total n that we have. And while it might, as a learner today, seem like this is straightforward, I get it, what's the big deal? The reality is that this is incredibly fundamental, not just to polynomial functions that we learned in high school, but to more abstract layers of algebra that you probably wouldn't see unless you study mathematics in college. So it's incredibly profound, but it also allows us to answer questions about polynomials that we might not ever know. But before we get to those questions, we have to talk about one more thing. This one more thing is called the Conjugate Pair Theorem. And this tells us if f of x is a polynomial with real coefficients, then if a plus bi is a 0, then a minus bi is a 0. So if f of x is a polynomial with real coefficients, and we know that a plus bi is a 0 of the function, then its conjugate, a minus bi, is also a 0. It's called a conjugate pair because all of our imaginary zeros of polynomials with real coefficients come in pairs. So with that second tool, we're able to analyze polynomial functions with incomplete information. So as an example, let's say f of x has degree let's say it has 9 and zeros 3i and 2 minus 5i. We're going to ask a series of questions about this polynomial that this is all we know about. So the first question, what are other zeros? Now, you might think we're not told any other zeros, so what can we do? And the reality is, because we have two complex numbers, their conjugates are also going to be zeros, because we're assuming that this has real coefficients, which I should have written down earlier. So we know if we have 3i, and we also have negative 3i, and if we have 2 minus I, or minus 5i, we also have 2 plus 5i. So we know 4 of these 9 zeros just because of the conjugate pair theorem. Now, you might also be wondering, at most, how many real zeros? Because for different applications, real zeros are places where this could actually equal 0. So if we had a polynomial describing like the height above Earth of a satellite, then we'd want to know the real zeros, because if the height gets to 0, our satellite has crashed into the Earth. So being able to know how many real zeros a function has is practical. So we know that it has 4 confirmed imaginary zeros. We don't know anything about the other 5 zeros, so it's possible all 5 of them are real numbers. So it has at most 5 real zeros, because 4 plus 5 adds up to 9. Now we can ask a slightly different question. At most, how many, I shouldn't say complex here, how many imaginary zeros? Now you might be tempted to say that the answer is 4 because it has 4 imaginary zeros, but we're asking about what's the maximum possible. So we know that there are still 5 unknown zeros, and we also know that imaginary zeros always come in pairs. I guess that does tell us at least our imaginary friends are always, with somebody, so they're never lonely, which is nice. But if we're talking about zeros, then we have 5 left. It's possible 2 of them make another pair, and it's possible the other 2 make another pair of imaginary numbers. But that last 0 could not be imaginary because it wouldn't be able to come in a pair. So at most, we have at most 8 imaginary zeros, because there has to be an even number. It's the maximum number of pairs that we could possibly have. So let's play around with this function for a moment. And I'm going to change the question so we can see another example. Let's say it also has our zeros 1 and 2. So we now know more of the zeros. We still know that it also has the complex numbers negative 3i and 2 plus 5i. But if we specifically go to that last question, what's the maximum number of imaginary zeros? Now, we know if we make our list of zeros, we have 6 here. So there's 3 zeros that are unknown. 4 of the known ones are imaginary. So if we look at this, only 2 of those 3 could be imaginary because we need 2 to make a pair. So we could have at most 6 imaginary zeros in total. The first 4 comes from the ones we're told in the conjugate pair theorem, and the next 2 comes from what those other 3 unknown zeros might be. So it's not always just the largest number of zeros, the largest even number of zeros less than the degree, because sometimes if we know real zeros, we have to bring that number down further. So these are some of the interesting, cool things that we can do with these theorems. In particular, it tells us two things. We can always factor every polynomial to a linear factorization, which allows us to very easily find the zeros of a function, the solutions, as well as the multiplicity of each root. It also tells us if we identify one complex number, then its conjugate is also a zero. So these two facts form a very powerful toolkit that allow us to factor every polynomial.